All right, so we're going to look at how you can figure out gravity anywhere, basically. This is our equation for gravity. Negative again because it's always pointed down. The g is a constant, 6.674 times 10 to the negative 11 meters cubed per kilogram second squared. The m refers to the mass of basically what's ever creating the gravity. The reality is that all of you have a gravitational attraction to yourselves. It's just that you're not very big. And so when you consider this constant is 10 to the minus 11 times your mass is not going to do much. But if you have a planet with a huge mass, then you can have an effective gravity that you would notice. And to several decimal places, here's what gravity would be for Earth, 9.8029 meters per second squared, or 32.162 feet per second squared. And of course, we have our equations of motion because if we're talking about things going up and down, uh, gravity slows it on the way up and speeds it up on the way down. So what we're going to look at are a couple of examples of basically dealing with gravity not on the ground or not on Earth. And so gravity would be different in that case. So in this first example, we have how high above the Earth's surface would you need to be to have a value for gravity of only 4.9 meters per second squared? In other words, about half of what it would be on the ground. So if we start off, again, this is our equation. And then, we're going to rearrange. And for these purposes, we're not going to worry about the negative sign because, again, that's just directional that it's pointed down because we're going to take our square root and we're not going to do square root of a negative number there. So, plugging them in. Mass, we're going to use the mass of the Earth here because we're talking about above the Earth's surface. And then, as I said, our gravity will be 4.9. And, just as a note, you can see some of the things that are getting canceled. So there goes our kilograms. There's the second part. 1 of the meters part is getting canceled. And so I'm going to square root eventually to find R. Square root of m squared, that'll give me meters for my distance. Yes. So there's the different units canceled. So let's go ahead and do that calculation real quick. And so basically our R squared and so we're going to end up That for R. Now, here's the deal. R is really that. In other words, it's the radius of the planet plus however high you are up in the air. So, what I want in this problem is how high, what's my altitude, so the number that we just figured out, there's my altitude. And let's see, what do we get? And, if we did a little rounding here, we could just say 2.64 times 10 to the 6 meters, or about a third, a little bit more than a third of the radius of the Earth out in space. So that's how high you need to be for gravity to be only 4.9. But a couple of key points again before we move on. First off, the R is the total distance from the center of the planet, if you will, to wherever you want it evaluated. So a lot of times we're just talking about on the surface of the planet. But if you are out in space, then it's going to be a little less. And of course, you could go even further. It's less and less. And effectively, you can get to a point in which there's not any gravitational attraction whatsoever. All right, second example. If Pluto, Mickey Mouse's dog, weighs 45 pounds on Earth, how much would he weigh on Jupiter? Please note Jupiter is 1,000 times more massive than the Earth, and roughly a little bit more than 10 times the radius. So, let's figure out what gravity is first. And again, my minus sign is just for the direction it's pointed towards the surface of the planet. And I might mention a very common mistake when you're figuring out gravity is don't forget that this is a squared term. Gravity is an inverse square law, meaning that if I go 4 times further away, or twice as further away, then I'm actually decreasing gravity 4 times because that twice the distance would then get squared. So let's see, what's our gravity? And the gravity for Jupiter is going to be basically 26. Now, we could, at this point, figure out how to go from pounds into newtons, which is a measure of force, but it's going to be proportional. So we can simply take 45 pounds and that's what it is for Jupiter. And we'll just use 9.8, close enough for the Earth. And so Pluto's dog would be 119 pounds on Jupiter. Which brings us to kind of a fundamental concept, if you will, the difference between mass and weight. We tend to think of them very similar because, of course, if we're on Earth all the time, then, you know, the mass is always going to be related to how much gravity is. The gravity is the same, and so we can always just kind of conceptually think of mass as being the same thing. But it turns out that weight is mass times gravity. And so the same size, the same volume, the same mass of an object is a lot bigger on Jupiter because gravity is almost 3 times. And so the mass or the weight becomes almost 3 times, 119.5 pounds for Pluto, Vicky's dog. The sun is like 30 times. It's like 30 times what it is on Earth. And so, instead of hundreds of pounds, it'd be thousands of pounds if you could literally walk on the sun. All right, in this third example and final example, we're going to look at an equation of motion problem that we've done before. Hey, we throw the ball up into the air. It's in the air for 3 seconds. So how high did it go? But the difference is, instead of being on Earth, where gravity is 9.8 meters per second squared, we're going to be on Mars. Mars is a little bit smaller than the Earth. It's a little bit less massive. Note 6.42 times 10 to the 23rd. Problem 1, Earth was 5.96 times 10 to the 24th, so not quite 10 times bigger in mass. In terms of radius, about half, 6.37 versus 3.38 times 10 to the 6 meters. So first thing we're going to do in this problem is, what's the gravity for Mars? So again, and as you can see, this does get a little bit old real quick. So gravity on Mars is 3.75 meters per second squared. Now that I have that, I can go ahead and solve my problem. If I think about, hey, I threw the ball up, so, half the time up, half the time down, which means I can use delta t. In this case, will be 1.5 seconds going down. If I'm just talking about the falling down, my VI would be 0 because, of course, it's got to come to a stop before it falls. So I have my delta t. I have my VI. I have my gravity. If I use my second equation of motion, in which first I don't have to worry about the first term because it stops before it falls. And we get 4.22 meters, which is not very much. 14 feet. Now, if you're like, well, what about the negative sign? Remember, that's just directional, so it's falling down. So I can talk about the 4.22 feet being, how far it fell. Or if I want, I can call it negative 4.22 meters because, again, it was falling downward. Gravity a lot smaller, about a third. So what, 3 seconds on Earth, you probably would have been talking about, let's see, 11 meters up, which would be about 35, 36 feet in the air. Here, not so much because gravity is so much less on Mars. So, an example of how to find an altitude, an example of how to consider weight somewhere else, and an example to do an equation of motion problem in which you're just looking at the vertical. Any questions?